section 3. Today we're talking about inscribed angles. Last section we talked about central angles, and we had said that a central angle is an angle whose vertex is at the center of a circle. So with an inscribed angle is when you have an angle with a vertex on the circle. So anywhere along the outside of the circle, if there's an angle that's created, it's called inscribed. So our example here, if you want to go ahead and draw this on your blank circle, we have center A and then points B, C, and D on the circle. So this ends up, if I was trying to name my inscribed angle, it would be angle BDC. And so that ends up being the inscribed angle. The intercepted arc is the arc that is captured by the inscribed angle. And so think of this sort of as the ice cream cone, that if this is the cone, where's your ice cream? Well, the ice cream goes up here. And so the intercepted arc of angle BDC is going to be arc BC. So we talked last section that central angles have the same measurement as the arcs that they intercept. Inscribed angles have a little bit of a different formula. Basically, the measure of the arc BC, is going to be equal to 2 times the measure of the angle. Or in other words, the angle will be half the measure of the arc. So if we take a look at some examples of how this might look. So this is sort of how we would solve it with the angle on the circle. So it could look kind of like our last example did. So if we had that angle 1 was equal to 50 degrees, and I asked you to find arc AB, so I want you to figure out what's this arc right here. So the idea is we use this equation, arc equals 2 times the angle. So I don't have the arc, so I'll just say arc AB is equal to 2 times, and then the inscribed angle is 50 degrees. So 2 times 50 is equal to 100. So that means that arc AB would be 100 degrees. Over here, this is another example where it's a tangent line meeting with a chord. So we sort of get this straight line here. Angles 1 and 2 form a linear pair. Therefore, they have to be supplementary. So if I gave you that angle 1 was 80 degrees, but then I asked you to find arc BCA. So BCA goes here, B to C, all the way around to A. So it's kind of the opposite of what I'm given. So there's a couple of different approaches you can take to this problem. One way is that if you know this is 80 degrees, you can do a linear pair and tell me that angle 2 would equal 100 degrees. I got that from doing 180 minus 80. So remember, linear pairs are supplementary. Supplementary means equals 180 degrees. So now if angle 2 is 100 degrees, now I'm going to use my formula of arc equals 2 times the angle, and 2 times 100 would tell me that arc BCD, a major arc, is going to equal 200 degrees. Another approach to doing that is that if you knew that this was 80 here, you can solve for arc BA. Oh, sorry, I said BCD, it should be BCA. You could say that arc BA is equal to 160 degrees, because 2 times the angle equals the arc. And then if you know there's 360 degrees in a circle, and if you found this part, you can just say, oh, 360 minus 160 gives me 200 left over. You still get the same answer of 200. So we're going through a couple properties here on what we can do with some inscribed angles. One of them deals with right triangles. If we have a right triangle inside of a circle, then we can say that the hypotenuse of the right angle, or of the right triangle, is going to be a diameter of the circle. So the converse of this is also true, which means we can get a biconditional statement. So if the measure of angle ABC is 90 degrees, or if and only if AC is a diameter. If AC is a diameter, then we can say that angle B is 90 degrees, and therefore we can say arc AC, this ice cream cone right here, is a semicircle, which we know again means it equals 180 degrees. If two inscribed angles of a circle intercept the same arc, then the angles have to be congruent. So for this particular example, we have angle D, which is right here, and angle C, which is right here. And if you take a look at the cone that is created for angle D, you get an ice cream or an arc of AB. Whereas if I switch that over and I look at the cone that is created for angle C, right there, we get that that cone is also intersecting at arc AB, or it intercepts that arc. So therefore, these two angles would have to be the same because they're intercepting the same arc. Okay, and then the last little theorem, I believe, is if we have a quadrilateral, again, quadrilateral 4 sides, inscribed in a circle. When it says inscribed, that just means that all points or all vertices are on the circle. That can be true if and only if the opposite angles are supplementary. So that would mean that E and G would have to add up to equal 180. That would mean that F and D add up to 180. So let's take a look at a couple of problems here and see how we kind of use this stuff to solve problems. So what I want to remind you is that for inscribed angles, its arc equals 2 times the angle. So here we're given that arc DB is 60 degrees in circle A. So that's telling us A is the center. They want us to find the measure of angle DAB and the measure of angle C. So if you notice here, DAB is a central angle. So that means that central angles equal the arc. That's what we talked about last class. So we can say if the arc is 60, then the central angle DAB is also 60 degrees. But now here, angle C, down here, that is an inscribed angle. And so we're going to use the formula arc 60 degrees equals 2 times the angle. So now this is one where we're given the arc, not the angle. So now we just work backwards through this and we divide by 2, and we get that the measure of angle C is equal to 30 degrees. Here, if we're given that QS is a diameter, find angle R. So if you just remember that property that, oh, if this is a diameter, then the opposite, this is sort of a hypotenuse, therefore this is 90 degrees. You can just say 90 and be done with it. But if you forget that idea and you just look at QS and you can say, oh, you know, it's intercepting this ice cream cone and this ice cream cone, it's 180 degrees, so that's a semicircle. So then you can just set this up again as arc equals 2 times the angle, and we get that the measure of angle R is going to equal 90. Here we have DC is 110 degrees. They want us to find the measure of angle A and the measure of angle B. Well, if you notice, DC, that's my ice cream, and the cone for angle A sort of intercepts that ice cream, whereas if you flip it over and look at angle B also intercepts that same arc DC. So this is one of those things where the two angles should be congruent. So that's kind of what I mentioned here, that angle A and B intercept the same arc, arc DC, so those two angles have to be equal. So now you can kind of set this up any way you want. I just worked with angle A. So we can say that 110 arc equals 2 times angle, so 110 equals 2 times angle A, and then just divide by 2. So if angle A is 55 degrees, then angle B also has to be 55 degrees. And then the last problems that we're going to look at here are those quadrilateral problems. So I want to remind you, opposite angles are supplementary. Opposite angles, the ones that are across from each other, are going to add up to equal 180. So you're kind of going to do two separate problems here. So you can say x plus 88 equals 180. Subtract 88, solve for x, you get 92. And then we're going to say y plus 100 equals 180. Subtract 100 from both sides, you get y equals 80. Over here, a little bit different, but same concept. So 3y plus 3y, 8x plus 4x. Again, opposite angles are supplementary. So here, 8x plus 4x equals 180. Combine like terms, you get 12x equals 180. Divide by 12, you get 15. And then this one, 3y plus 3y equals 180. 6y equals 180. Divide by 6, you get y equals 30. Alright, that is it for section 3. Thank you for watching. I know it, and now you know it.